Morning, everyone. Questions while we wait for others to come in? Anybody? How are we doing with the material there? We said the midterm was next week, right? Andy, what is the issue with web work? Oh, is it factoring? The amount of attempts does not affect your web grade. The midterm will be distributed via CrowdMark. So for those of you not familiar with CrowdMark, it's a delivery system. You'll get an email. Yeah, so Andy, click on email TA in that question so I can access your web work. It was finicky for a few people. I'll fix it for you. So back to the midterm. 72. You'll have 72 hours, right, to do it. Distributed through CrowdMark. You'll get an email, and I mean, CrowdMark, if you've never used it before, it's very user-friendly. Essentially, what you do is you'll do the work on paper and take a picture of the work and upload it to CrowdMark. That's it. Questions? We're good? Moving on? Or back to what we were doing last time, namely complex numbers. Right, let's recap what we saw, since it has been a week. You don't have to sign for CrowdMark. I import the class list from my courses directly. So you're signed up automatically. And as I said, you get an email once the exam has been released, and you can just follow that to the exam. So in our discussion of complex numbers last time, we asked the question, is the quotient of two complex numbers itself a complex number? And we saw the answer to that, the answer being yes. And we saw how to deal with that. And let's take this as an example to remind ourselves, is this a complex number? Can we write it in the form a plus ib? You know, Jean-Pierre is asking if you can use LaTeX for the midterm. Please don't use it. I want to see handwritten work. So write everything on paper, take a picture. It's all good. So is this a complex number? If so, what is the real part of this expression? What is the imaginary part? And we saw that by multiplying by first of all, multiplying by 1, namely the conjugate of the denominator divided by itself, right? You multiply by 1, you're not changing anything. And this allows you to rewrite the expression. What happens, let's expand. So 2 minus I plus 2I minus I squared. And the denominator is 4 minus 2I plus 2I minus I squared. Or if you prefer, I squared is minus 1, so this is 3 plus I over, you see that these two things cancel out, and that's exactly what happens when you multiply by the conjugate, right? You get the modulus squared, so 4 plus 1 is 5. Or this is 3 over 5 plus I 1 over 5. So the real part would be 3 over 5, the imaginary part, 1 over 5, something you couldn't really tell just by looking, right? It's not clear what the real and imaginary parts are without actually doing the work. Very nice. Now, before we continue, let's think back to how this whole discussion of complex numbers arose, right? We had observed that this polynomial has no real roots, right? No real roots. In other words, x squared is minus 1, and x was plus or minus the square root of minus 1. This is not a real number. And we asked the question, what happens if you throw in that imaginary number? And that gave us, right, if we set I to be the square root of -1, that gave rise to the set of complex numbers. A plus IB, where A and B are real numbers. Right, so, and in particular, if B is 0, you see that all the real numbers are themselves complex numbers. So this gave us an extension, if you will, of the complex numbers. An immediate question that arises, can this be repeated? If you have another polynomial, perhaps a polynomial with complex coefficients, can you find a root of that which isn't in the complex numbers, give that root a name, maybe call it J or something, right, like we did here, right? Square root of -1 is not a real number. We gave it a name, I, and we made the set A plus IB. Can we repeat that? If you took a polynomial with complex coefficients, is there a root which isn't in the complex numbers? And can you throw that in and get something larger and larger and larger? Does the process keep on repeating? It's a valid question. It's a very good question. The answer is no. The answer is no, and comes to us via the fundamental theorem of algebra. I had already used that name previously in the context of polynomials, where I said every polynomial factor is a product of irreducible polynomials. Here, so that wasn't the real definition of the fundamental theorem of algebra. Here's the real one. Every complex polynomial, so every non-constant polynomial with complex coefficients has a root in the complex numbers. Right, so every polynomial, every non-constant polynomial with complex coefficients has a root in the complex numbers. This means that in the realm of complex numbers, the only irreducible polynomials then would have to be polynomials of degree 1. In other words, everything factors completely into polynomials of degree 1. This property is known as being algebraically closed. So the complex numbers are algebraically closed. You can also see that this implies the previous definition of the fundamental theorem of algebra that I had written down, right? A weaker theorem, right? If polynomials, if non-constant polynomials always have a root, then it follows that the only irreducible polynomials can be of degree 1 or 2, right, in the real numbers. Because as we saw, if you have x minus z times x minus z conjugate, this has to be a real polynomial. We work that out. So, conclusion, all the roots of polynomials with complex coefficients have to be complex numbers themselves. Let's take an example. Consider this polynomial. If we search for the roots, I mean, it's easy to see that x squared is 1 plus I, so x is plus or minus the square root of 1 plus I. But this is a polynomial with complex coefficients, so this must have complex roots. This, the square root of 1 plus I, must be a complex number. Square root of 1 plus I must be some complex number. So it has to be, we have to be able to write it in the form a plus ib. What is a? What is b? Well, let's solve. Let's solve for AB. Let's solve for the real and imaginary parts of the square root of 1 plus I. Let's square both sides to get rid of the square root. And here, what is that? This square, this times 2. And plus this square. 1 plus I squared, of course, you know, would be -1, so this is a squared minus b squared plus I 2ab. And now what do we have here? Here we're saying that this complex number, 1 plus I, is equal to this complex number. So let's take the real part of both sides. If you do the same thing to both sides, equality is maintained, right? This number is equal to that number, so the real part of this must be the real part of that. What is the real part of the left-hand side? It's easy to see that the real part on the left is 1. Real part on the right, you can read it off. You know what it is. Real part on the right is a squared minus b squared. Do the same thing, but with the imaginary part. Imaginary part on the left, 1 again. Imaginary part on the right, 2ab. So what do we have here? We have 2 equations, 2 unknowns. You can solve however you wish. Do we want to solve for b here? Right, from this one, we get that b, isolate for b, bring the 2a to the other side. b is 1 over 2a. Plug that back into here. b is 1 over 2a. So we had a squared minus b squared. So a squared minus 1 over 2a all squared. Or this is 1 over 4a squared. Whatever you want to do, either put everything over a common denominator, or maybe you want to get rid of the denominator here, which you can do by multiplying the whole equation by 4a squared. If you do the same thing to both sides, equality is maintained, right? So we'll multiply by 4a squared. 4a squared times 1. 4a squared times a squared. You know what happens to the exponents. We get 4a to the 4. And 4a squared times 1 over 4a squared, or 4a squared over 4a squared. That is just 1. Does everybody see that? Everybody with us? How are we doing? Questions? Let me give you a moment. Everybody comfortable with this? Excellent. So what are we doing? We're looking for a and b. And now we have an equation involving A. We want to isolate for A. Let's bring the 4A squared to the other side. And we get 4A to the 4 minus 4A squared minus 1 is equal to 0. Not immediately clear what we can do here. Does anybody see it? How do we solve for A? How do we isolate for A? Not very nice, very nice. Rashad has suggested to make a change of variables, let x be A squared. Right? So that A to the 4 is x squared, and this becomes 4x squared minus 4x minus 1 equal to 0. Very nice. And then, as Rashad has suggested, what you have there is a quadratic equation. A polynomial, a quadratic function, quadratic polynomial, polynomial degree 2 equal to 0. We're looking for the roots, right? What values of x make this 0? You could try to factor, and if it's not working out, you know you can always resort to the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Very nice. Let's clean this up. So if we clean that up, that is 4 plus or minus 4 times 4 is 16. The minuses cancel, and we get plus 16, so that is root 32 over 8. 32 is 16 times 2. So if you take the square root of 16 times the square root of 2, square root of 16 is itself 4. We can factor out a 4 from the numerator. And we're left with 1 plus or minus root 2 over 2. Very nice. Now, as you know, root 2 is 1.4 something something. And the x was actually a squared, right? So this x is actually a squared. So a squared is this. And consequently, a has to be the square root of this. But root 2 is something bigger than 1, right? 1.4 something something. So if you had the minus, 1 minus 1.4 would be a negative number. And that is not possible since you have something positive on the left. So the negative is out, and thus we have to restrict our attention to the positive number in this case, the positive square root. right? Because negative square root would make the whole thing negative, and that's not possible. Because you know a is a real number. So a squared has to be positive. And consequently, a is plus or minus the square root of 1 plus root 2 over 2. So if we take the positive, right, because all we were asking for was a square root. So if you take a to be this, then b which was 1 over 2a, is therefore 1 over 2 square root. Is therefore this. You can leave it as is, or if you want to simplify, you can take square root of the top, square root of the bottom, then this times this cancels out nicely. So you could rewrite it this way if you wanted. Well, I mean, leave it as that. I'm very happy with that. And there it is. The square root of 1 plus I can therefore be written as this plus I 1 over 2 root. Here we took the positive square root. You could, of course, repeat with the negative, right? Or if you did it with the negative, you would get this as well. Question arises, why not plug this into a calculator, get a decimal number, and use that? The problem is, as you know, calculators only give you an approximation, right? We showed when we were talking about prime numbers that root 2 was an irrational number. We proved that, right? So root 2 has a decimal expansion which neither terminates nor repeats. So this, in decimal form, is going to go on forever. So this number is going to go on forever in decimal form. And what the calculator will give you is an approximation to that, not the actual number. Whereas here we have the actual number. So for the midterm, you should avoid decimals. In fact, you should always avoid decimals. How are we doing? Questions? We're good? Why don't we try another example? few questions here. Is there an easier way to find the complex form of root of complex numbers? Easier? I don't think so. Well, it actually depends what you mean by easier. So here, I claim that this was rather easy, a lot of work. Right, so Rashad now is suggesting shorter instead of easier, and shorter, yes. Yes. You can use the fact, you can use Euler's formula. Right, we saw that you could write every complex number in the form r e to the I theta. For some r and theta. And consequently, if you're taking the square root set, which is z to the 1/2, then it's r to the 1/2 e to the I theta over 2. And you're done. That's it. So that was fast. But of course, you need to know what that is. In other words, you need to know the modulus of the number. And you need to know the angle that number, that ray makes with the positive x-axis measured counterclockwise. But I don't want to get into that, because that uses quite a bit of trigonometry and this and that. And it's beyond us only because we didn't spend any time on it. I mean, if we had gone into that idea, and if we had developed that idea, you would have seen that it's not any harder than what we were doing. But yeah. So don't use that on the midterm. Should a question like this arise, I'm not saying it will, but it might. You want to do it the long way, which is relatively easy as well. Consider this. Factor this into a product of irreducible polynomials. First of all, what are we talking about? This is a polynomial with real coefficients, right? So when we mean irreducible, we mean irreducible in the sense of real polynomials. Because irreducible under the idea of complex numbers is really meaningless, because you know everything factors completely. So this would just be a product of polynomials of degree 1 in the complex numbers. We mean irreducible of degree 1 or degree 2 with no real roots. I'm sure you understood that. Wait, Ali had a question as well. Sorry about that. Can you explain this business? Well, we had started by saying that the square root of 1 plus I had the form a plus ib, and we solved for a and b. A was this, and b, which was 1 over 2a, is that. So we're just putting everything together at the end for completeness. Factor this into a product of irreducible polynomials. There you go. So first of all, what is the degree of this polynomial? You know it's a polynomial of degree 4. Consequently, you know that it's not irreducible, right? The only irreducible polynomials are polynomials of degree 1 or degree 2 with no real roots. This is a polynomial of degree 4. You know that it reduces. Moreover, since it's a polynomial with only real coefficients, if, right, I mean, let's give this a name, let's call it px. We saw that if z is a root, so is z conjugate. Right? So if you're given a complex root, you know that its complex conjugate will also be a root. So in this case, since 3 plus I is a root, so is 3 minus I. You don't have to check it. You know that it's right. And if you do x minus 1 root times x minus the other, we also saw that this was going to be a real polynomial. Let's do it. It's not a formula I want you to learn by heart, but at least know what's going to happen. You get x squared, then you get minus 3 minus I times x, and then minus 3 plus I times x, and finally plus 3 plus I times 3 minus I. So let's expand everything. We get a minus 3x plus ix minus 3x minus ix plus 9 minus 3i plus 3i minus I squared. Let's simplify that, see what's going on. What is that? X squared remains. Minus 3x minus 3x is a minus 6x. The ix and minus ix cancel. The minus 3i and the plus 3i cancel. I squared is negative 1. So this becomes plus 1. 9 plus 1 is 10. And there we have it. A polynomial of degree 2 with only real coefficients, exactly as expected. And this must be a factor of that. So now we can do long division. X squared minus 6x plus 10 into 2x to the 4 minus 3x cubed so let's do long division. What must we multiply to x squared to get a 2x to the 4? I think it's clear that it's 2x squared. So this times this. And this times that. So that minus that is 0. This minus that, I want to say 9x cubed. Is that correct? And this minus that. We'll bring down the next term. What must we multiply to x squared to get a 9x cubed? We need a plus 9x. And repeat. Minus 54 x squared and plus 90x. This minus that is 0. This minus that, I want to say minus 5x squared. And this minus that, 30x. Bring down the last term. And repeat. What must we multiply to x squared to get a minus 5x squared? We need a minus 5. Minus 5x squared. Minus 5 times minus 6 is plus 30x. And finally, minus 15. And you see that these are exactly the same. So when you subtract them, you get a remainder of 0, exactly as expected. Conclusion. Conclusion. This polynomial factors as x squared minus 6x plus 10 times 2x squared plus 9x minus 5. We know that this is irreducible because we know what the roots are, right? The roots are 3 plus I and 3 minus I. So this is irreducible as the roots are 3 plus I and 3 minus I. So it's got complex roots. What about this one? It's a polynomial of degree 2, so could be irreducible. Might not. We have to check. So, is this irreducible? It's a polynomial of degree 2, so let's find the roots. Negative b plus or minus square root of b squared minus 4a c all over 2a. So 2040. So minus 9 plus or minus square root. What did we say? 40. So 121. Square root of 121 you recognize to be 11. So minus 9 plus or minus 11 over 4. Could we have factored that nicely? Of course. Right? I mean, maybe you already saw it, but didn't want to speak up. Of course, this simplifies. Well, first of all, we found the roots. We know they're real, but I think it's clear. I think it's clear that this factors as 2x 2x minus 1, x plus 5. Is that right? We get a 10 minus 1 is 9. There it is. So the roots would have been 1/2 and minus 5, which is probably what we're going to get here, right? Minus 9 plus 11, that is 2/4. Or minus 9 minus 11 is minus 20/4, which is minus 5. Exactly as suggested. Here it is. So this one is irreducible of degree 2, but this one factors into polynomials of degree 1. How are we doing here? Questions? Let's end this discussion of complex numbers with one last property. Of the complex numbers, or rather, a property which the complex numbers lack. In the real numbers, if I give you two real numbers, it's usually very easy to say which one is larger than the other. Right? If I give you 3 versus 4, well, I mean, it's clear that 4 is larger. Even if the numbers aren't immediately clear. How did you get 2x minus 1? And that's a question which arises often, right? And sometimes on the web work, people are getting the answers wrong because of that. The quadratic formula will give you the roots, right? Here it gives us the roots 1/2 and minus 5. And now you're thinking to yourself, well, isn't this going to factor as x minus 1/2 times x plus 5? The problem is it doesn't, because if you were to expand that back, you get an x squared here, not the required 2x squared. How do you circumvent that? Factor out a 2. You're missing a 2. Now everything's going to work very nicely. Right, so multiply the whole. If you want to do x minus the root times x minus the other, you need to multiply by the coefficient of x squared. Because just having these two things doesn't give you this back. The roots agree, but the polynomials themselves do not. Multiply by the coefficient of x squared, and you're good to go. So here, if you want, you can multiply it into this one to get rid of the fraction, and that's where you get your 2x minus 1 from. Right? I mean, here I'm giving you two numbers, 2/5 versus 3/7. Just by looking, it's not crystal clear which one is larger. But you know that you can put them over a common denominator, maybe a common denominator of 35. So this is 14/35 versus 15/35. Right here you multiply by 7/7. You multiply by 1, you're not changing anything. Here you multiply by 5/5. You multiply by 1, you're not changing anything. And now it's clear which one is larger. Right? This one is the larger of the two numbers. This property of the real numbers is called a total order. Given two numbers, either they are the same number or one is larger than the other. Right, so given two numbers that are not the same, one has to be larger than the other. This is called a total order, or the real numbers are totally ordered. The complex numbers do not have this property. If I give you two numbers, you cannot necessarily say that one is larger than the other. The complex numbers are not totally ordered. Consider I versus 0. Two complex numbers. So what's going to happen? If the complex numbers were totally ordered, either these two numbers would be equal, or this one would be bigger than 0, or this one would be less than 0. In other words, one of them, if they're not equal, one of them has to be bigger. So here's the first question: is I equal to 0? I mean, I think you know that it isn't. How do we prove that it is not? If you multiply both sides by I, what do you get? I times I is -1. And I times 0 is 0. Now, if you weren't convinced that I was not equal to 0 in the complex numbers, for sure you know that -1 is not equal to 0. -1 is not equal to 0. Right, so this is a contradiction. So I is not 0. Well, okay. Maybe it's bigger than 0. If it is, multiply both sides by I. Since I is bigger than 0, the inequality is preserved. You're multiplying by something that's bigger than 0. And what do we get? I times I is -1 again. And I times 0 is 0. So you get -1 is bigger than 0. You know that to be false. Contradiction. So I is not bigger than 0. The only other possibility that remains is if I was less than 0. So if I is less than 0, bring this to the other side, and we get that minus I is bigger than 0. Multiply both sides by minus I. Since minus I is bigger than 0, the inequality is preserved. Minus I times 0. On the right-hand side, we get minus I times minus I. Minus minus is gone. I times I is I squared, which is -1. And we get 0 is less than -1. Again, or -1 is bigger than 0. Again, a contradiction. So I is not less than 0. So I is not 0, it's not larger than 0, and it's not less than 0 either. In other words, C is not totally ordered. What does this mean? Well, it means that when you take a square root of a complex number like we did, we cannot talk about the positive square root or the negative square root, because those concepts don't make sense in the set of complex numbers, right? Because we would think of the positive square root as being the square root which is bigger than 0, but that doesn't make sense here. Or the negative square root as the square root which is less than 0, but that doesn't make sense with the complex numbers. So when I gave you the two roots, of 1 plus I as this and that, so that was one square root, and this was the other. It's very tempting to call this the positive square root and this one the negative, but that doesn't make sense. Because you don't have that total order. This thing is not going to be bigger than 0 versus this one, which should be less than 0. That doesn't happen here. You could say that this one is the negative of that one, but we're not going to call this the positive square root. Books circumvent that issue by asking for the square root where the real part is positive or where the real part is negative. But there it is. Questions? Questions on complex numbers? This ends the discussion of complex numbers. And this ends the material for the midterm. So midterm will include everything up to and including today's lecture. Questions? Anybody? Very good. So thank you all for coming then. You guys have a good weekend. I will see you on Monday. The midterm is not timed. You have the entire 72 hours. It's going to be very short. You'll have plenty of time. And if you know the material, everything will go very well. You guys have a good one. I'll see you on Monday.